Okay, so this is the exam review session for exam 2 for the extra practice exam 2 that I have uploaded on Google Drive. Um, Once again, we'll try to finish up these problems as soon as we can and then hopefully try and leave it open for questions at the end. Um, and just to help me out to do that, like I'm just hoping that you guys will be like active. Like if I ask a question, like just try as best as you can to pay attention. I know sometimes we can all zone out. I personally zoned out last night at the very end with that last problem, but um, yeah, just try and stay alert as much as possible. I know we all had classes today, so I totally understand if that's not you know the case all the time during the session, but yeah, just stick with me, please, so we can try and finish this thing quickly. Not to rush, but to just have open time for questions at the end if we can. But yeah, I'm gonna go ahead and start labeling here problem 1. So problem 1 is electric potential, right? It says point charges Q1 equals 2 microcoulombs, Q2 is negative 2 microcoulombs, are placed as shown in the corners of a 3 centimeter side square, right? It says calculate the electrical potential at points A and B, right? So let me go ahead and draw this real quick. You have Q2 over here, and that is the negative charge, and Q1 over here, and that is the positive charge, right? And then you have points A and points B, and they want you to calculate the electric potential at every single, or not every single, but just those 2 points, right? And this distance here between Q2 and A is 3 centimeters, and this distance here between Q2 and Q1 is 3 centimeters, right? So they're essentially asking for you to find out what VA is and what VB is, right? So at point A, let's just observe point A here real quick. Whenever they're asking you to find the electric potential at a specific point, number one, you have to realize that that specific point is usually, right, referring to the convention that at a point we're looking at things to have be a positive test charge, right? That's generally the convention that we're using. If they're just referring to something as being at point, usually that's a positive test charge. That really matters more when you have like electric fields that you're trying to calculate, right? So your direction of the electric field at a specific point will be based on the convention that we're using positive test charges, right? So you draw them in a way to describe how a positive test charge would move relative to those charges, for example, right? So if I had point A here, if this was a positive test charge, right, then actually I want to just get a laser thing real quick. Okay, so if we have point A here, right? So if this was a positive test charge, it would tend to move towards that negative charge like that. So that would be the direction of the electric field in that sense. If we have a positive charge over here, then that positive test charge would move this way along that direct axis, right, away from Q1 to be repelled by it, right? So that's generally kind of the convention that we're using. But with electric potential here, we're concerned with only and only the source charge, right? So we're not concerned with what this point could be, whether it's positive or negative. We're only concerned with the source charge, right? So the charges that are generating an electric field, the charges that are going to give us some kind of electric potential. And those are Q1 and Q2. And if you go and reference your equation sheet on the exam, you'll be able to see that on that equation sheet, the equation for voltage, the electric potential V, is equal to KQ over R, right? And that KQ over R, that Q right there is capital Q, or uppercase Q, right? And those uppercase letters will define the source charges, the charges that are generating the like electric field or electric potential, right? So we're not concerned with a possible charge at point A. We're only concerned with the charges Q1 and Q2 and what kind of electric potential they're generating. And Matthew, I think the file would be Google Drive exam 2 folder, and then what's it called? Practice exams, I think. And then extra practice 2 is what it's called, I believe. Let me double check just so I'm 100% sure. Yeah, so exam 2 review folder, then practice exams, and then extra practice 2. Yeah. But yeah. So with this equation here, right, generally, just for V, it's V equals K big Q over R, right, where this uppercase Q, once again, is the source charge. So the idea here at point A is that you have two source charges that are going to be generating electric potential, and at point A, that electric potential at point A is going to be affected by both of those charges. It's going to be affected by both charges generating their own electric potential, right? So VA should be the sum of both electric potentials from Q1 and Q2, right? So it's just a matter really of just plugging things in, right? So you have K Q1 over the distance between like Q1 and A. So we can call it R1A. And then plus KQ2 and the distance between Q2 and A, right? So R1A is the distance between R1, or my bad, not R1, but point A and Q1, and then R2A is distance between A and Q2, right? And so the distance that we're talking about is the direct distance along the axis between those two points. So here's Q2, here's point A. That's the direct distance, that's the shortest distance between them, and that distance is 3 centimeters, right? However, for Q1, right, there's a distance here, distance there, right, to get to point A. We want the shortest distance, which would be the direct distance between them, which is this hypotenuse here, right? We want this direct axis here, the direct distance between them. And so you can figure that out using Pythagorean theorem, right? You have 3 centimeters here, 3 centimeters there, 3 squared plus 3 squared, right? And then take the square root of that, that would give you this distance right here, right? And so, let's see here. Also, make sure that your answer for your distances are in meters, right? Because absolutely got to be in meters because we have to have things in SI units. So don't forget to do that, right? So you can say like 0.03 meters, because that's 3 centimeters squared, plus 0.03 meters squared, square root that, and that gives you your R2A, which is your distance between, or R1A, my bad, distance between Q1 and point A, right? And this value, I believe, should be, what is it, 0.03 square root 2, I guess. We can just do that. I don't have the calculator on me, but actually, hold up. Let me just type it out here. So this should be like 0.042, something like that. Yeah, 0.04, roughly. So this distance here is 0.04, and that's your R1A. And then 0.03 is your R2A, right? Because that's just the 3 centimeter distance between Q2 and A. That's really all you have to do. So you know your K is your 9 times 10 to the 9th. And then your Q1 obviously would just be the charge of Q1, and that's 2 microcoulombs. Once again, we got to convert it to coulombs. We got to make sure everything is in SI units, so 2 times 10 to the negative 6. And then you can divide that by your R1A, so that was that 0.04. And then add this to your other KQ2 over R. So this is 9 times 10 to the 9th. And then, let's see here. So this is a 2 times 10 to the negative 6 coulombs, right? This is coulombs as well. And then divided by 0.03, right? So what do you think I'm missing here? I did this on purpose, just to see if you guys are paying attention. What am I missing from this equation here? No, we don't have to square the R, because the voltage equation is just KQ over R. Something else is missing. Take a look at the charges. There we go. What about the charges do you notice is different, or that's wrong? Exactly, right? So the equation, if you see it on the equation sheet, there's no absolute value sign around the Q, right? So we have to include and have to be wary of the charge. So this charge, right, this was the negative charge that we denoted, right? This was R1A. This is the distance between, or not this one, my bad. The other one. So R2A, right? So Q2 is negative. So we have to include this little negative sign here to make sure that this all works out. And so you should end up with like, I'm going just by the key, I think. So it's negative 1.7 times 10 to the 5th volts. I'm not 100% sure if that's entirely correct or not. I have seen some mistakes on the quizzes and the answer keys for the, what's it called? The exams. So take this like final answer with a grain of salt, but this work is correct. But yeah. So that's VA. VB is pretty much the same idea. So I'm going to skip doing VB just because, you know, like I said, it's just going to be the same idea. I can just explain it kind of verbally real quick. So once again, it would be like KQ1 over R1 plus KQ2 over R2. But now it's the distance between B and Q1 and B and Q2. So B and Q1, what would be the distance between it? What's the distance between B and Q1? Right here. 3 centimeters, right? So 0.03 meters. And B and Q2, this direct distance, is just going to be the same idea. Once again, you take your 3 squared, right? Or in this case, this way. And then that's your hypotenuse, right? So just use the same equation here again to get your distance between B and Q2, right? And so, I don't know why this is sticking around. This is an error. There we go. That's a bug. Or not. I don't know what's going on here. There we go. So, once again, VB, do the same thing. What else did I want to say for this? Yeah, so someone had a question about when you use KQ1, Q2 versus KQ over R squared. Well, it's just dependent really on the context of what you're doing, right? So KQ1, Q2 over R squared, that is your electrostatic force equation, right? KQ1, Q2 over R squared is your electrostatic force. Your energy equation is KQ1, Q2 over R. So it's like the force equation, but the R is squared. And then your voltage, right, your electric potential is just KQ over R. Now, the reason for all of this, like why they all look the same and why you don't square in certain cases and why you only have one Q in certain cases, just comes down to the definition of all of these. Every single one of these equations has been derived from the electrostatic force equation. There are like, so the equations are, it'll take a while to just kind of like go through the derivation for each one. How you get from the electrostatic force to the electrical potential energy to your voltage and all of that, and your electric field even, but they're all interrelated with one another. And so it's just a matter of looking at, okay, what value am I looking for? I'm looking for electric potential. Okay, I just use KQ over R. And Q, that big Q, is my source charge. So I'm not concerned with charges at that point. So theoretically, if they gave you a charge here, a positive charge, and they gave you the value for it, I don't care about it. I only care about what this point feels from the other charges around it. I don't care about what that test charge, what that point charge there is generating. Right? I'm only concerned with everything else around it. Does that make sense for like when you kind of like use each one? I mean, really just depended on what they're asking, but I mean, I can just, like I said, I have the equations derived in each of the slides that I have the PowerPoints on Google Drive to show you like how each one is kind of developed. But if you are still kind of confused about it, I think the reading does a really good job about showing you how you go from force to energy and all of that. Like, but yeah. And then if you were looking at like KQ over R squared specifically, that is electric field of a point charge. And you can see that like on the equation sheet. Large Q, source charge, right? If they have the two lines here, they're asking for absolute value, right? So I don't include signs in my equation if that's the case. Little q is point charge or test charge. And I think that should be it, right? But yeah, negative 150,000, someone said they got that for A. So that's about the same, like negative 1.7 times 10 to the fifth is about that. I think, yeah, 1, 2, 3, 4. I think so. 1, 2, 3, 4, 5. Yeah. So it might be like I said, the answer might be a little off, but if you have everything else, like all the work and everything correct, then you should be okay. But is everyone confident that they'll be able to do VB as well? VB would pretty much be the exact same thing. I'm going to go ahead and set up problem 2 while you guys give me an answer as to whether VB is okay. Okay, looks like it's fair for everybody else. All right, let's see here. So problem 2 now, it says work to relocate. It says in the previous step or previous setup, a charge Q is equal to negative 3 microcoulombs. That's positioned at point A. Calculate the amount of work required to relocate the charge Q to point B. Right, so we want to relocate. See, this is exactly what I was talking about here, where they gave you a charge, negative 3 microcoulombs, they put it at A. If they were to do that, like in this problem 2 here, we do not care about that charge. We only care about the electric potential that point A feels, right? What it feels at point A because of Q1 and Q2, because of the electric fields that they're generating, because of the electric potential that they're generating. If they were to assign a charge there, we do not care about it, right? This case, in problem 2, now we kind of want to care about it because we have to do some other stuff with it, right? So if we have this Q, it's negative 3 microcoulombs, right? Positioned at point A. They want us to calculate now the amount of work, right, required to relocate the charge Q to point B. So we want to move this charge to point B from point A, right? So effectively, when you're doing work, if you remember from Physics 131, you know that you'll have some conversion of energy, right? Energy has to be conserved, but energy is converted from one type to another. If we're moving something from point A to point B, we should have kinetic energy, right? Because there's movement, obviously. However, if you look at the change in kinetic energy, if you start off, right, so we know that this is the work energy theorem. Work is equal to the change in energy is equal to the sum of kinetic energy and let's say this electrical potential energy here. We're never really dealing with gravity or anything else here. So you started off at rest at point A, and then you end up at rest at point B. So really your initial and final velocities would be 0. So your kinetic energy is usually 0 here, right? unless, right, we did an example problem with this yesterday on the practice on that first extra practice exam, where they were moving a charge from a specific point to like infinity, and at that point, like, you're not really allowing that charge to rest, so you would be able to find out the final velocity for it. But in this case, we're moving it from one specific point to another specific point, from rest to rest, right? And so your kinetic energy change would be 0, and we're left with some change in the electrical potential energy, right? So this electrical potential energy change, we can calculate it, right, and account for it, and therefore calculate the work, because we have an equation that says Q times the change in the voltage to get from one point to another will give us our electrical potential energy change, right? So this little q, once again, it's referring to a point charge, a test charge, something that we're trying to test like the electric field of other charges with, right? So we know Q1 and Q2 are generating their own type of electric potential and their own type of electric field. We place that charge, in this case they put it as capital Q. They really shouldn't do that. It should be lowercase q, because you're effectively testing, right, the difference in electric potential between point A and point B, right? So it should be little q. They put it as capital Q, but you have to recognize or understand that what we're doing, like the context of the problem, is that we're testing the difference between two potentials, between two electrical potentials of different charges, right? So this delta V is going to be, obviously you have point A and point B, right? So this is like your VF minus VI. Well, your final position was point B, and your initial position was point A. So there's a specific electrical potential that you're experiencing, that -3 microcoulomb charge is experiencing at point A. And then when you move it from point A to point B, that -3 microcoulomb test charge is also experiencing some electrical potential at point B, right? So it's VB minus VA, and this little q right here refers to that test charge that we're testing the difference in electrical potentials with, right? That -3 microcoulomb charge. So once again, microcoulombs, we have to convert it to just regular coulombs, so -3 times 10 to the -6. And if you look to the equation, you'll realize that that little q doesn't have an absolute value sign around it, so we are concerned with the sign, so you plug in the sign, right? So you plug in that negative sign there. Now, VB minus VA, right? You would essentially just take your answer from VB in part A, or problem 1, subtract VA from it, that you also got from problem 1, and then you should be able to get that delta V, and then from that, you multiply it by the test charge, and you should be able to get your work done, right? And that'll be equal to the change in the electrical potential energy at that point. I believe the answer for VA and VB are actually the same. They're going to be identical, pretty much. It's just that one is positive and one is negative, it seems. So VA was negative, VB was positive, if I'm not mistaken. But the same magnitudes, essentially. So you take -3 times 10 to the -6. I'm going by the key here, but it says it should be positive 1.7 times 10 to the 5th volts for VB, and you're subtracting negative 1.7 times 10 to the 5th volts for VA, because we got VA was negative 1.7. I think some of you guys got negative 1.5. That seems about right as well. It might just be a difference in whether you used 0.04 for your distance for R1A or 0.042. Like, it just kind of depends, I guess. But I would double check your work as well, just to make sure that you have all the work correct, like I have it here. But yeah, essentially you just take your VB from part A, or from problem 1, minus VA from problem 1. That's your delta V, and you multiply it by your test charge. You got negative 0.9 joules for this. I have from the key negative 1.02. So difference is kind of like, small here, but like I said, I'm not sure 100% about the accuracy of this answer key. So if you have all the work correctly and you're following this methodology, you should be okay. I have a question here that says, so kinetic energy is equal to 0 because it's going from rest to rest. Exactly, right? So we're setting up this charge here. It's positioned at point A. It's not moving. And then we move it, and then we just relocate it to point B. So it started off not moving. It ends up not moving. Initial velocity 0, final velocity 0. So essentially your kinetic energy change would be 0, and then that allows us to just be concerned with the change in the electrical potential energy. And that allows us to solve for the work done to move that charge from point A to point B. Does that make sense? And then your answers would be in joules here because of energy. Yep. And then while you guys ask some questions, I will set up problem 3. Okay. Are there sometimes, I have a question here. It says, are there sometimes problems where they have us include kinetic energy? Is that mostly rare because I haven't seen it a lot? Or maybe I just can't recall those types of questions. We actually had one last night, if you remember. Let me pull it up. I'll tell you exactly which problem that was so you can kind of reference it. Let's see here. So that problem was problem 8, part C, where we had an electron and that negative point charge. And you essentially just had to find out the final speed of the electron. So you knew that initially it was speed of 0, right? VI was 0. But VF, because you move that electron an infinite distance away, then we haven't relocated it to a definite point, so it hasn't stopped yet, right? Because infinity is infinity, right? You don't stop. So then we're essentially calculating the velocity at infinity, and that's like a weird concept, but at that point, that would be the only point where you would be able to technically like calculate a final velocity because you haven't stopped yet, because you can't really reach infinity. So, but that would be the kind of context that we would be looking at to solve for kinetic energy. But you're right, we haven't seen a lot of problems like that. I highly doubt that would be something that would pop up just because it's kind of a weird concept, but be prepared for it. That extra practice exam 1 was actually the exam that I took as a student. So that popped up on my exam. So, like, just make sure you kind of prepped for it. That's the context, like, keep an eye out. Like, that's the context that we would be looking for. You start off at a point, and then you go to infinity. So you start off stopping, you're at rest, but you haven't gone to rest because you can't go to infinity technically, right? So at that point, you would be able to calculate a VF. And so to do something like that, and we already did that last night. If you go and check back the video, right? Essentially, you look at like EI is equal to EF. You set your initial and final energies equal to each other because of conservation of energy, right? You'd have some initial electrical potential energy, and your initial kinetic energy would be 0 because you started off at rest. But then at infinity, you would have no electrical potential energy because the equation for electrical potential energy is KQ1 Q2 over R. And so if your R, your distance away from a source charge, is infinite, right? If infinity is in the denominator, then you just approach 0. So this UEF would be 0, but your KF, because you haven't stopped yet, that would be a specific value. So you essentially set up your electrical potential energy at that initial point equal to half mvf squared. And that's how you would do it. But that's an excellent question. Yeah, exactly. And then you can isolate the VF by itself and solve for your final velocity at that point. Does that make sense? Awesome. So if there aren't any other questions, I can move on to problem 3. So problem 3 is capacitors. I went in depth with capacitors and resistors last night with circuits and all of that. Just to kind of ask, because it's been a day pretty much, did that analogy of tree branches to describe circuits in like capacitors and resistors and circuits in series and parallel, did that analogy of using trees make sense? Or was that more confusing? Okay, it makes sense. I don't know. I think it seems like we have the same group of people from last night. for the most part. But do you guys want another rundown of this whole like idea of trees like being used as an analogy to how circuits or resistors and capacitors in series and parallel work? Okay, you weren't here for last night's session. Okay, yeah. So, let me see here. Let me first of all try and grab like what I did last night with this capacitors and resistor stuff, and then copy this down. So copy. I hope I can just paste it normally. Or not. Okay, well, screw it. It's fine. Or hold up. Can I? No, I cannot. All right, it's fine. So the idea for these circuits is, let's start off here with a very simple type of circuit. We have a battery here, right? What do I want to say? So this is your positive terminal, this is your negative terminal. You might have a resistor here. And then I don't want to erase the whole thing. I want to like have, partial eraser. There we go. And then we have this branch, right? So I like to call it a branch. And another resistor here, for example. Right? R1, R2, R3, and then R4, right? So the idea that I came up with a couple of days ago to explain, or better explain, like circuits, resistors in series and parallel, stuff like that, is to use trees, right? So if I have this tree, right, keep in mind the only thing I can ever draw, only thing I learned how to draw well in elementary school and middle school is trees, right? So do not roast my trees, because I take pride in how I draw them. So here are your roots, right? This is not just, anyway. So here are your roots, right? Your roots will act as the battery, providing a source of electric potential, right? As you go up the trunk of a tree, that trunk, plus all the branches that make up that tree, right, will act as your wire, right? The idea is that as you go up this trunk, you'll have branches, right? Sometimes you'll have regular branches like this, right, that won't really have any branches of their own, right? So you'll just have like a branch like this, and that's it. That's the branch. Cool, done, right? But a lot of the times, and this is way more often, way more common, is that you'll have a branch, right, that'll come up here, that'll branch off into its own set of branches, right? So here's that initial branch, and then it branches off here, like that, right? So here is where I can explain it and relate it to a tree, right? So we start off with the roots, the battery. Let me grab a little laser tool here. So here are the roots. Oops, I don't know why that's not writing. There we go. Here are the roots. Here's the battery, right? And this is going up the trunk, right? Here it's going up the trunk. And now, when we encounter a resistor like this is what happens. We get to this branch here, right? Okay, resistor is connected directly to the rest of the trunk. Here's that branch without any other additional branches. Awesome, right? There's that branch that we want. It's connected to the rest of the trunk, right? Perfectly seamless, perfectly consecutive, like a TV series, right? Where you have episodes in chronological order, connected to one another, consecutive, they all make sense, they all continue, right? There's no tangents that go off, right, in different episodes. Like everything kind of seems connected to each other. And that's the same thing with a tree here. You go from the trunk to this branch here, no extra branching off anywhere else, right? It's all very consecutive, very seamless, very continuous, right? Now we continue along. Let's say now we are on that same branch, right? But now we experience an extra branching point, right? This is a branching point right here. Formally, it's called a junction, right? Formally, it's called a junction, but I like to call it a branching point because this is effectively where the current, right? The current that is supposed to be carrying charge from the battery is splitting off into different resistors, right? It is now going up here or down here, right? So the current is being branched off, being split off into different branches, right? So we had the trunk, now we moved up to a branch, and then we're going into a branch of a branch, right? So this is pretty much what's happening here, where we have this branch, right? That's our R1 resistor, and now we've reached this branching point, that junction, where now we could go into R2 or R3, right? That's the idea of resistors being in parallel. Whenever you see a branching point, right? Whenever you see a branching point, that junction like that, where the current is clearly being split off into different directions, then you know the resistors on those like sub-branches, if you will be in parallel. So R2 and R3 are in parallel with each other because they allow for the current to be split up into different pieces, right? So if you came out with 6 amps here, right? 6 amps goes through that R1, it's consecutive, it's seamless, it goes through that branch, right? From the trunk to that branch, still 6 amps here, but then it gets split off. Maybe 4 amps go up here, 2 amps go up there, right? Maybe you have like a longer branch and just a shorter branch, right? But the idea is, and this is where kind of the analogy kind of breaks off, because I don't think you would be able to see this in real life, I don't know. But effectively, these branches are going to reunite at this output point. So here's like an input, here's an input, and here's an output. And the idea is that they want to conserve the charge, they want to conserve the current, right? So if I go in with 6 amps, 4 amps might be split up at top, 2 amps might be split up to the bottom one, but the idea is that when you come out, you have to have that 6 amps once again, right? So resistors in series are going to be like a TV series, right? They're going to be consecutive, chronological, next to each other, continuous, no branching in between them. Resistors that are in series with each other will be continuous with one another with no branching in between. So we cannot say, for example, that R1 and R2 or R1 and R3, right, would be in series with each other because there's a clear branching point here at this input point between them. There is a point where the current splits off. The current is not continuous between them, so they are not in series with one another. So the goal with simplifying circuits and the goal with all these problems is to get every single thing, capacitors or resistors, in series with one another. That is the goal, right? So I encounter a branching point and I'm like, okay, well, now the current is split off. I don't want it to split off. How can I create a combined resistor or a pseudo combined resistor that would replicate the resistance of both of these resistors in one, and then that pseudo combined resistor would be in series with R1? Well, the idea is something called effective resistance, or equivalent resistance, equivalent resistance. And so as Matthew pointed out, for parallel resistors, in order to find the equivalent resistor, right, the resistor that would be equivalent to, that would be the combined version of R2 and R3, is you would take 1 over R equivalent, right? So R equivalent, REQ, is the equivalent resistance that we're looking for. So essentially you just take the sum of the reciprocals of the resistances of each resistor in parallel. So we have 1 over R2 plus 1 over R3. R2 and R3 are in parallel with one another, right? So we add up the reciprocals, and then that sum is equal to the reciprocal of the equivalent resistance. So if this was 2 ohms for R2 and 3 ohms for R3, right? Then, so this is 3/6, right? and you have 2 6, so 5 6, right? That's the sum there. But 5 6 is not the resistance of the equivalent resistor, that pseudo-combined resistor. That's not what it is. It's actually 6/5, because remember, 5 over 6 is only equal to 1 over R EQ. So we have to multiply this over, right? And then simplify it to be able to get the R EQ alone. So you would actually just take the reciprocal of your sum to get the actual equivalent resistance, which is 6/5, right? And so at that point, we would reach a circuit that looks like this, where we have that R1, and now we have a resistor, a pseudo-combined resistor that's called R23, right? That's how you write it. That's the notation where you combine a resistor like that. You write all of the resistors that have been combined together as a subscript, R23. And then you have R4 down here. Now everything is in series. Everything is consecutive. When I go from R1 to R2 to R4, or R23 and R4, there's no branching off of my current. There's no splitting off anymore anywhere in between, right? The current is completely consecutive, right? Everything is connected. Everything is one. Everything is unified, right? That's the idea of looking at things between, like, figuring out if something is in series or in parallel, right? If there's branching off of some kind, there's parallel, right? If there's no branching off, those two resistors are in series. And so the way I like to do things is that if there are multiple branching points, every time I encounter one, I simplify it, right? And then I start back at my battery, right? As soon as I simplify one, I go back to my battery, retrace my current, okay? I've simplified it. Okay, well, what if there was, before R4, right? Before R4, what if there was like another branch, right? There was another branch here where it's like, let's call this, what if R4 was part of a branch, like R4, R5, and then we had R6 over here, right? Then I'm like, okay, well, I just simplified R23, right? I just simplified R2 and R3. Those were parallel with each other. I simplified them down into a parallel circuit, or into a series circuit, or not circuit, series resistor, right? R23, a pseudo-combined resistor with R1. And now I'm going through the circuit again, and I'm like, okay, well, there's another branching point. So I have to simplify R4 and R5 using that equivalent resistance equation. And I would simplify it down to a pseudo-combined resistor, an equivalent resistor, right, called R4, R5, right? And so then I would have R4, 5, be in series with R6, be in series with R23, be in series with R1, right? They're all in series with one another, and you can just add them up, right? Because there's no branching off of the current between any of these resistors. Now, some people might ask, like, well, what if you have resistors in series in parallel? Which, that just means, like, what if I had this branching point, right? And here's a branch, right? This is like branch 1, and this is branch 2, right? What if I had along this second branch not only R4, but I also had, like, let's say, let me adjust the values here, right? So what if this was R4, but then I had R5 over here, and this was R6. What do you notice about R4 and R5? They're part of the same branch, branch 2, but what about them? What do you notice about R4 and R5? Are they in parallel or in series with each other? Series, excellent, right? Do you want to explain why they are in series? Or are you a little unsure? Yeah, exactly. They're next to each other, right? They're consecutive. There's no branching between R4 and R5, despite there being like limited space, really, because it's a branch, right? That branch too. But there's no splitting off between R4 and R5. The current hasn't split anywhere, right? So they're consecutive, they're continuous. So R4 and R5 are in series with one another. So you could actually simplify them down into an equivalent combined resistor or pseudo combined resistor called R45, right? And then R45 and R6, those would be in parallel with one another, right? Because there's clear splitting off between here and here. And so then you can once again use the equivalent resistance equation here with resistors in parallel, where you could do 1 over R45 plus 1 over R6. And then this would just essentially combine to, let me just use the whole eraser now. This would effectively combine down to R4, 5, 6. Exactly. R4, 5, 6. Your subscript should be just all the resistors that have been combined in that branch. Right? And then R1, R2, 3, R4, 5, 6, and then you can just adjust this to R7. Those are all in series with one another, and you can just add them up, right? To find the equivalent resistance of two resistors or multiple resistors in series, instead of doing 1 divided by R equivalent is equal to 1 over the resistance plus 1 over the other resistance and whatever, for the equivalent resistance of series, it's just, let me just write this as parallel. This is in series. You just add up the resistors. So R1 plus R2, 3 plus R4, 5, 6 plus R7, and that gives you a combined resistor, pseudo-combined resistor, that would be called R1, 2, 3, 4, 5, 6, 7. All the resistors in the system, in the circuit combined, that would be the equivalent, because they're all in series with one another, and so they can just be easily added up. But yeah. Same exact concepts of series and parallel will apply to capacitors. But yeah. With respect to capacitors and resistors, there's different rules for them, and that's what I wanted to copy down earlier. Instead of just copying it down, honestly, I'll just kind of look at this again, because this document is uploaded on the Google Drive as well. So resistors, if they're in series with one another, right, like I said, you would just simply add up the resistances together, R1 plus R2 plus R3, whatever, right? As long as those resistors are in series, you can just add them up to find the equivalent resistance, right? Once again, because they're consecutive with one another, they're like a TV series, like episodes in a TV series. They're consecutive, they're chronological, they're continuous, right? There's no branching off or tangents between them, right? Then the current or the charge that's delivered between resistors in series has to be the same, right? There's no branching off of the current anywhere, so the resistors in series would have to have current be the same between them. And then, for resistors in series, you would add up voltages between them, right? So each resistor in series, right, if we go back to the that problem there, each one of these resistors is going to have what's called a voltage drop, right? And a voltage drop is like what the name suggests, a drop in the voltage as a result of that resistor, right? The resistor is supposed to be, as in its name, right, it's resisting charge, right, or causing a voltage drop. So let's say maybe 24 volts is being delivered, right? That's the electric potential of the battery. 24 volts is being delivered by the battery. Well, maybe, we know V equals IR, if I calculate, let's say I know that the current delivered is 6 amps, right? I know that the current delivered is 6 amps. So if this was 2 ohms, right, then 6 times 2, this is I and this is R, 1, right? Then that means there's a voltage drop, 12 volts, across this resistor. So the voltage is effectively decreased by 12 volts. So 24 volts minus 12 volts, now you have 12 volts left over, right? Each resistor is going to have a voltage drop to where by the time you reach the end of the final resistor, it's like you have no more voltage, and then you go back into this negative terminal, to the positive one, and it's like quote unquote recharging the electrical potential, right? So now you go back to having that 24 volts. So resistors in series, you would add up the voltage drops, right? Now, resistors in parallel, the voltage is the same across every single resistor in parallel, right? So if you have resistors in parallel like this, R1, R2, and R3, they're clearly branches, right? Then the voltage is actually going to be the same across them. So let's say you have 12 volts going in that I was mentioning earlier, right? Then, what do I want to say? So let's say you combined R1, R2, and R3 together, and then you combined any other resistors left over and whatnot, right? And now you're looking at like a combined resistor called R1, 2, 3, right? And you know that the current going through that one should have been like 6 amps, right? Let's say the combined resistor was like 3 ohms or something. So 6 amps times 3 ohms gives you 18 volts. Let's say it was more than 24 volts that was being delivered by the battery. Let's just say that. Well, that 18 volts, right, should be the same voltage across every single resistor. Like this resistor should have a voltage drop of 18 volts. This one should have 18 volts. This one should have 18 volts. The voltage drop is not split between them, right? So it's not like it's because we know after simplifying the resistors, let's say if after we simplified them, we figured out that the combined resistor had a voltage drop of 18 volts. Well, it's not like this resistor had 6 volts, this one had 6 volts, let me actually just so I can have different values. Let's say this one had 5 volts, right? And then this one had 7 volts. The voltage drop is not being split between these resistors, right? 6 plus 5 plus 7 would give you 18, right? The voltage drop is not being split between them. Rather, every single one has that same voltage drop of 18 volts, right? And the reason for that is that, like, what do I want to say for this? Formally, on either side, they have the same common input point and the same common output point, right? They're all kind of branches of this point right here and this point right here. So they're all connected with one another. And so that connection, that common connection on either end, causes the voltage to be the same across every single one of these resistors in parallel, right? And at the same time, right, we know that the current is the only thing that's being split between them, right? And so for the current to be properly like split off, the voltage has to be the same across every single one. And then if you know V equals IR, right? So if it's 18 volts, you divide by the resistance, and that gets you the current that was split off at that point, right? So the idea is that because of that common connection between them, all of these resistors in parallel would have the same voltage across each one. The voltage is not split off, only the current is split off. But yeah. Once again, to find out the equivalent resistance of resistors in parallel, you add up the reciprocals, and that's equal to the reciprocal of the equivalent resistance, right? So just by doing 1 over R1 plus 1 over R2 plus 1 over R3 doesn't get you the combined resistance yet, because whatever that is, 1 over, let's say, 5, right? That's only equal to 1 over RP, or the equivalent resistance, right? So the actual equivalent resistance would be 5. So it would just be the reciprocal of that final answer. And then across, like I said, across those 3 resistors, the current is split up, and so the current has to add up between those resistors. So if I'm coming in hot with 6 amps, 2 might be delivered up here, 1 might be delivered down there in the middle, right? And then the other 3 might be in the bottom. The current has to add up. So that's the gist of resistors, series, and parallel, and how to calculate them. Series and parallel, same idea for capacitors. It's just that for capacitors in series, right? You're going to add up the voltage once again. But instead of adding up the capacitors in series just normally like C1 plus C2 plus C3, you're adding up the reciprocals. So whatever you do for a resistor, you do the opposite for a capacitor, basically. And the same concepts apply, essentially, right? So current has to be the same for capacitors in series. That means that the charge, because current is charge over time, right? And so charge has to be the same for capacitors in series. And the voltages have to add up, right? Same thing for parallel. The voltage is the same across every single capacitor and every single series, or every single resistor in parallel, right? So the same like concepts apply, but the math differs. Whatever you do for a resistor is the exact opposite for what you do for a capacitor. So resistors in series, you just simply add them up. For capacitors in series, you add up the reciprocals, right? For resistors in parallel, you add up the reciprocals. For capacitors in parallel, you add them up normally, right? Now, I think that's probably all I wanted to say, and that's kind of like the gist of my spiel about circuits in general and how you can relate them to like trees and branches and stuff like that. Does that make sense overall? I'm really hoping that was beneficial to just gain a better understanding of this stuff. It seems like people are having their minds blown, so I guess I don't know if that's a good sign or a bad sign. But I mean, if you have the concept down of like how to like figure things out, whether they're in series or parallel, you're fine, because then the math is really the concept is the hard part. The math is the easy part. So it's a matter of just like memorizing what to do now whenever you encounter a series capacitor or resistor, or series resistor or parallel of each one. But does that make you more confident then to solve something like problem 3? So problem 3 is what? So problem 3 here is capacitors, right? Calculate the equivalent capacitance for the arrangement shown. So let me copy this. So here's the capacitors, right? Are these capacitors in series or are they in parallel? Series, excellent. They're consecutive, they're continuous, there's no branching between them, right? How do we add up capacitors in series then? And the good thing is like the equations for all of these and even the concepts like are in the equation sheet actually. So how do we calculate the equivalent capacitance for capacitors in series? Oh, well, I wrote it down already. Yeah, exactly. Nice. You're already typing it, so we're good. So yeah, 1 over C1 plus 1 over C2 plus 1 over C3, and then boom, you're done, right? So this would be 1 over 1 plus 1 over 2 plus 1 over 3, and that should give you 11 over 6, right? I believe so. Yep, 9. Yep, 11 over 6. And then that's equal to 1 over the equivalent capacitance. So equivalent capacitance is equal to 6 over 11 then. Right? That's in farads, units of farads. And you're done. Right? So that's problem 3. Problem 4 is nothing. Okay. I did not account for that. That was not on my bingo card. All right. One less problem to do, I guess. Problem 5. I don't know what that's all about. Problem 5, ion current. It says calcium ions each carrying a charge of plus 2 E, right? E would be charge of an electron, or a proton for that matter. In this case, it's a proton because, or a positive charge essentially, right? Because it's positive there. So flow through an ion channel, calculate the current through the ion channel if 120 ions pass through it in 50 milliseconds, right? So it wants us to calculate the current. The equation for the current is actually the change in charge divided by the change in time. It's kind of like speed or velocity. It's like the amount of charge going through a specific area per second. So how can you figure out the amount of charge going through here? We know that there are 120 ions, right? There are 120 ions. What charge does each ion carry? What charge does each ion carry? Yeah, 2 times the charge of an electron, right? So essentially, you would just multiply because you know that for every ion per ion, right? Essentially, this is how it's going to be written out. Like, for every ion, right? Your ions cancel out with your ion. You have a charge of 2 times the charge of an electron. So that's your numerator, and then your denominator is just the time, right? So the 50 milliseconds, which is just 50 times 10 to the negative 3 seconds. So you would essentially find from your equation sheet the charge of an electron, and that is like 1.6 times 10 to the negative something. 1.6 times 10 to the negative 19 coulombs, right? 2 times that would give you the charge of a single calcium ion, and you multiply by 120 ions to get the total charge among those 120 ions, divided by the time it takes for that amount of charge to go through, which is 50 milliseconds, or 50 times 10 to the negative 3 seconds. And then that's equal to your current. And I'm going by the key once again, and it should be 4.8 amps, right? Or coulombs per second. And that's pretty much it, right? Very one and done, easy problem, easy 3 points right there. I would very much would have liked to have this exam when I was a student, because 3, 4, and, well, not 4, 3, 5, and 6, like, are very just plug and chug, easy point questions. In my opinion, at least. Like, you can see here, like, we only used one equation. We didn't have to, like, simplify anything down or use, complex stuff or trig identities or anything like that. No, this was not my actual exam. My actual exam was the one from last night. So, do you get a lot of points off for using the wrong units? If you have everything else right and you just mess up the units at the end, I don't think like it's a huge amount of points off. Maybe like 1, maybe half. It just depends on how they've assigned the units or how they assign the points for that. But I don't think it's like a lot, because what's more important is like actually doing your stuff correctly. But yeah. And then problem 6 now is asking about resistivity. So there's a concept of resistance and there is resistivity. Resistivity is the inherent like resistance. I don't want to use resistance again, but basically it's like the resistance built into a material, right? So let's say, for example, you have a wire, right? Generally in these problems, wires don't have resistance, right? Or they're having negligible resistance, so we don't factor them in like with the other resistors and stuff. But let's imagine that it has resistance, like a wire, like a copper wire or something has resistance, right? Well, for that wire, right, it has an inherent resistance, like a built-in resistance based on the material that we're using, right? So copper might have a specific resistance, tungsten might have another resistance, iron might have another resistance. It depends on what material that we're using, right? So the inherent built-in, if you will, resistance of a material is called its resistivity, right? But the resistance in general, right, would just be like, okay, well, what if I took a very long wire, right? Now I'm looking at, a very specific amount of copper wire. So I know, like, copper wire, let's say the default, I'm just talking in a very informal sense, but just to kind of explain this. So let's say the default amount of copper wire is 3 centimeters long, right? That is basic foundational copper material, right? That basic foundational copper material has a resistivity of 3 times 10 to the negative 6 ohms. Ohm meters is what resistivity's units are actually. Ohm meters. And so that's the inherent built-in resistance, if you will, of the material. What if I told you, okay, how about what's the resistance, not resistivity, what's the resistance of a 6-meter long copper wire? Well, now we're getting specific, right? Now we're not dealing with that foundational material. Now we're dealing with some specific amount, right? So that's the difference between resistance and resistivity. Resistivity is this inherent resistance kind of built into the material itself, and then resistance is like, okay, for a specific amount, like, okay, how resistant is this material, or how resistant is this wire now, right? So at first we were talking about how resistant is the copper itself, the material. Now we're wondering, okay, how resistant is this wire, right? So that's the idea of resistance and resistivity. So now here they're asking for resistivity, right? They're saying the resistivity of a material is rho is equal to 3 times 10 to the negative 3 ohm meters. So resistivity is ohm meters, and resistance is just ohms, right? So that kind of goes back to my idea where it's like resistivity is like per meter or something, or like something non-specific, but resistance is like, okay, if we multiplied it by how many meters, then we could get, the resistance of the whole thing. This is very informal. Once again, I'm just trying to help you better understand, because they both start with R. They both like have the same root, resist, right? So it just might get confusing to figure out the difference between them. So hopefully that kind of clears it up. But now they're saying a resistor with a square cross section of 2 millimeters by 2 millimeters and a length of 50 millimeters is made from the material. Determine the resistance of the resistor when current flows as shown, right? So now we're just trying to figure out the resistance. They gave us the resistivity, right? There's an equation for resistance with this resistivity stuff, and that's the resistance is equal to the resistivity times the length of the material, or the length of the wire, or whatever, divided by the cross-sectional area, right? So we have our resistivity, and that's 3 times 10 to the negative 3 ohm meters. We know our length, that was 50 millimeters, and that's the same as 50 times 10 to the negative 3 meters. And then we have our cross-sectional area, right? Cross-sectional area was that square that they told us about, 2 millimeters by 2 millimeters. So we know that millimeters would just be 2 times 10 to the negative 3 meters, right? So 2 times 10 to the negative 3 meters times 2 times 10 to the negative 3 meters. Or you can just take 2 times 10 to the negative 3 squared, right? Because we want to figure out the area. 2 times 2. 2 times 10 to the negative 3 times 2 times 10 to the negative 3. So that's your cross-sectional area. That's your length of your resistor or your wire, and then times your resistivity right there. And that gives you your resistance. And that should be like 37.5 ohms based on the key that I'm going by. I don't know if that's right or wrong, but this is the work that you should have shown. Does that make sense for a difference between resistance and resistivity? Okay, awesome. We can go to problem 7 now. Right. Problem 7, electric field and forces. A particle with charge Q is equal to 2 microcoulombs, and that's 6 centimeters away from a large sheet that has a charge density of sigma is equal to 200 microcoulombs per meter squared. So Q, 2 microcoulombs, and then sigma is equal to 200 microcoulombs per meter squared, right? And this is the setup that we have where it's just like this sheet charge right here, a bunch of positives, right? And then this little Q here that's located 6 centimeters away from the sheet charge, right? That's it. That's the information that we know, I think. Or they have, I don't know if they have point A. Here is 4 centimeters. I think that's it. 4 centimeters and 6 centimeters there. So part A is asking us to determine the magnitude and direction of the force on the charge Q. Right? Force on charge Q. Well, if you remember what I was talking about yesterday, and if you've read my slides, then you know that this notation is very common. Force on something by something, right? So this is the force on charge Q, this little charge here, by something else. What is causing the force on charge Q? Basically, with forces like electrostatic forces, you can either think of a charge being repelled or attracted to, basically. So what's causing the repulsion or the attraction of Q? The sheet, right? The sheet has positive charges, so we can assume that it's probably going to repel the charge, and so the charge is going to go to the left, right? So it's just going to move away from it, right? That's the force that charge Q will feel by the sheet, right? So force on Q by sheet. What does this notation mean? There's a really easy way you can kind of figure things out, right? And I mentioned this in my slides, where it's the way you can rearrange this is that you can say or think about this as, what does Q feel, what does the charge feel, right, by the other thing, right? So commonly, right, we might have like force of Q1 on Q2. So this is basically saying, like, what does Q2, or how does Q2 react to Q1, right? How does Q react to the sheet? Does that make sense, this notation? How does Q react to sheet? How does Q2 react to Q1, for example? Does that make sense? Okay. So for this force that's going to be caused, right? I mean, if you think about it, we know what an electric force equation is. It's KQ1 Q2 over R squared, right? But are we really dealing with 2-point charges? We're not, right? We have a point charge, capital Q right there, but we have a sheet charge, right? So this sheet charge is supposed to be generating what? A uniform electric field. Bravo. Excellent. Right? So there's a second equation that will help us figure out the force, right? And that is the force at a specific point, right, is equal to that test charge at that point times the electric field generated at that point, or felt at that point, right? So the force that Q feels by the sheet, right, is determined by the identity of the charge, Q, times the electric field generated by the sheet, right? You can find that equation on the electric field like heading on your equation sheet. Another way they've kind of written it down on the equation sheet, and this is really helpful to see, is that the electric field at a specific point is equal to the force of the field on the test charge, right? Field on test means how does the test charge react to the field? How does Q react to the sheet? Divided by the test charge itself, divided by Q itself, right? So you just multiply this over, EQ is equal to F, right? So boom. We have the identity of Q, that's 2 microcoulombs, but we got to figure out the identity of this electric field. So how can we figure that out with a sheet charge? Well, a sheet charge has this formula, right? And it's also under the electric field heading in your equation sheet. And it's the absolute value of sigma, remember it's absolute value here, divided by 2 times the permittivity constant, right? So they gave us the sigma value, which was 200 microcoulombs per meter squared. We want to convert that to be in SI units, so 2 times 200 times 10 to the negative 6. That would be coulombs per meter squared. And then divide that by 2 times the permittivity constant. Permittivity constant is located under the physical constants heading on your equation sheet, and that is 8.85 times 10 to the negative 12 coulomb squared per Newton meter squared. And then that's how you can get your electric field. Once you have that, I'm basing this on the key, but you should get like around 11.3 times 10 to the 6th. Once again, if the key is not matching up with your work, then it's probably a typo, but if as long as you have this work correct, you should be okay. So that's your electric field, and now it's just a matter of plugging the electric field back into that equation, right? So force is equal to that charge, 2 microcoulombs, so 2 times 10 to the negative 6 coulombs, times that electric field, 11.3 times 10 to the 6th newtons per coulomb, and that gives you your force. Once again, going by the key, but it's 22.6 newtons, as far as I know. And then they want the direction, right? So the direction should simply be directly to the left, right? So this point is pretty much perpendicular with the electric field. So we know that electric field for positive charges is always going to point outwards away from the charge. So it's going to point this way. So at that point, right, we can see that this would essentially be the electric field right there. E sheet would be right there, like that. Directed perpendicular to the sheet and in line with the charge right there. But yeah. So that's A. Part B is asking, well, point A is located 4 centimeters above the charge. Determine the magnitude and direction as an angle with the horizontal of the electric field at point A. Well, at point A, you kind of have a dilemma. At point A, you not only have... actually, I'll just leave this for you guys to understand this part. So, at point A, what would be... Essentially, this is asking, like, once again, we're asking for a specific point. We're looking at what this point feels. What does this point feel? What is it going to be feeling? What does point A feel? Yep, exactly, right? So it'll feel an electric field generated by the charge itself as well as a electric field from the sheet itself, right? So what direction would the electric field be pointing in that's generated by the field, by the sheet at point A? What direction would it be generated by the sheet at point A? No, you're right. Yeah, exactly. Pointing to the left like that. That's for the sheet, E sheet. Right? But what about the electric field of the positive charge here, the Q? What direction would that be pointing in? Exactly. It's because we assume the convention is that whenever we're talking about a specific point, that it's always a positive test charge, right? So because we're assuming, and that it's not really assuming, it's because the convention is using positive test charges, you're drawing the line in a way that would essentially show how a positive test charge, if it were there, how it would react to the charges. So if you have a sheet that's a bunch of positive charges together, and you place this point A, if once again, by the convention that we're using positive test charges, A would go flying to the left, right? So based on the idea that we're assuming A has a positive test charge at it, then what direction should the electric field of Q be pointing in? So here's Q. How would A react to Q? It would be repelled, but what direction would the repulsion occur in? Would it go to the left, downwards, to the right? What's going on here? How would point A react? Like, imagine if there was a positive charge at point A. What direction would the point A charge be flying in? Exactly, up, right? Because if this was positive as well, this was positive, it would just go flying away from this charge, right? So always draw it in a way of how that charge would react, relating to a specific charge. Now, out to the left diagonally would be the net way how that charge would react, because we have E sheet like this, and then EQ like that, right? So that the charge, if it were a positive charge at point A, would go flying upwards in response to Q. So it's kind of like motion up and to the left, basically. So you're exactly right, out to the left diagonally. So we kind of have to do some like vector addition of sorts, right, to figure this out. So we effectively have an X and a Y component of our electric field, right? The electric field would kind of go this way, E net. We want to figure out what E net is. We want to figure out the direction, the angle, right? So we know that E sheet, figured that out from before, and we're assuming that this is right, is 11.3 times 10 to the 6 newtons per coulomb. And that's to the left, right? So that, in and of itself, that is our X component right there, right? But we have to adjust this. We have to adjust this to be negative. Why is it negative? Because it's pointing in the negative X direction, right? We want our EX to be negative because it's pointing in the negative X direction. So, let me just write this down, negative, because negative X direction. Right? Now, EQ, right, that would essentially be our Y, EY basically, right? This is our EX, and this is our EY, our Y component. So this EY, we can calculate it, or this EQ, we can calculate it by taking K, absolute value of Q, right? I believe that's the, yep. So the electric field of a point charge, you can find that under the electric field heading on your equation sheet. It's K times the absolute value of the charge that is causing that electric field, the source charge in this case, capital Q, divided by R squared, the distance between point A and that charge, right? So 9 times 10 to the 9th, and then multiplied by that charge, that's 2 times 10 to the negative 6 coulombs, right? Because 2 microcoulombs, and divided by R squared, and that is 4 centimeters, so 0.04 squared, because the distance between A and that positive Q charge is 4 centimeters, right? And that gives us EY or our EQ here. And it just so happens to be that it's the exact same value, actually, 11.3 times 10 to the 6 newtons per coulomb, at least based on the key. I got a negative 11.3 times 10 to the 6, so we calculated the charge of the sheet, or the electric field of the sheet, and that was 11.3 times 10 to the 6, at least based on the equation, or based on the key, I mean. And so I added a little negative sign because the electric field is pointing to the left along the negative x-axis. Does that make sense? Yep. So once we have this EY, we have our EX, right? Now it's just a matter of finding E net. So if this was E sheet to the left like that, right? And EQ upwards like that, right? Then we're essentially finding this net, E net, the hypotenuse, right? So we're using Pythagorean theorem, right? So E net squared is equal to EX squared plus EY squared, right? And then E net is going to be equal to the square root of both of these. So one is going to be negative 11.3 times 10 to the 6th. We square it, doesn't matter because the square will get rid of the negative sign, and then 11.3 times 10 to the 6th. And then you get your E net. And your E net should be like 16 times 10 to the 6th based on that. Or like based on the key. Now, how can we figure out our angle? This angle theta here. How can we figure out the angle? Exactly, right? Inverse tangent of the y component of the electric field, the net electric field, and divided by the x component of the net electric field. So EQ over E sheet, basically, and take the inverse tangent of that, right? And then that should give you, like, apparently 135 degrees. Based on the key. But yeah. Does that sound good for B? Okay. Let's see here. So we have part C now. It says there's a point B where the electric field vanishes. Show on the picture where you expect point B to be located. So this is more of just a conceptual type problem here, right? So, what do I want to say? Let me redraw this real quick. So, we have this sheet charge, or not. Sheet charge here, positive, 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 right? And then we have this Q. And now we want to figure out where the electric field would vanish, where the electric field is essentially 0. Vanishes just means 0, right? And now you have to draw where point B is located. Okay. First of all, we have to analyze or understand something that's very important, and that is, does the electric field of a sheet charge change with distance away from the sheet? You sure? No, right? Because based on the equation, electric field for a sheet charge is sigma over 2 times your permittivity constant. Nowhere do we have radius here anywhere, right? There's no distance that factors in yet. It's only dependent on sigma, only dependent on the charge that we have with the sheet, right? And the cross-sectional area, or the area of the sheet itself. That's it, right? So I could literally be over here, over here, over here, wherever, right? And I would still have the same magnitude of my electric field. But the electric field of a point charge does depend on the distance, right? And so, what do I want to say here? Yeah. So, also for positive charges, the electric field is pointing in what direction? Assuming a positive test charge for a convention. How do the electric field lines generally point for positive charges? Do they point inwards to the charge? or do they point outwards to the charge or from the charge? Just in general, positive charges in general. Outwards, right? So it'll look something like this for the electric field lines of Q. Right? And for a sheet charge like this, right, it's still outwards, but it's all kind of like perpendicular to the charge. So it'll look like that. So understanding these concepts is very important because it allows you to draw this, right? You want the electric field to be fully canceled out. You want E net to be 0, right? Based on these drawings, if I were to place a point anywhere here, let me do a different color here or something. If I placed a charge here, or charge there, or charge here, or charge here, or charge here, or charge there, wherever, right? Where do you think, which point could I place a charge at where the electric fields would cancel out? And by canceling out, effectively, the directions of each one, right? How the charge would respond to each sheet and charge, how like it would respond like going up, down, left, right, how would it cancel each other out? Like here? Like here? So if we assume that this sheet also has lines going like this, right? And we're assuming this point B is a test charge, a positive test charge, right? And we know that Q will have lines pointing outwards, then B would pretty much just fly all the way to the right. You see what I mean? So I see a couple people actually got it. Between Q and the sheet charge. Excellent. Perfect. So where exactly between them? Like here, or exactly between them, like directly between them, like along that same axis? Directly between, right? So this charge right here. Why? Because you can see if I place a positive test charge here, and this is positive, well, then the positive test charge is going to get repelled by that Q. At the same time, you have another positive over here. And that positive test charge is going to get repelled by the other sheet, right? So we're not sure exactly, what distance it is away, yet at least. But we know it has to be between here, right? Because the vectors of the electric fields are going to perfectly cancel out. You're going to have one that's going to the right and one that's going to the left. Where you put it, right, will depend on the magnitudes of the electric fields generated by the sheet and by the Q. But if we were to put it here, for example, then you have it being repelled by the sheet this way, but you have it being repelled by the charge that way. So the X components cancel out, but now you have a Y component. You see what I mean? Does that make sense, Eric? Like any other point, it would have some Y component. We want to make sure that the X components perfectly cancel out. Because really, this sheet charge is only dealing with X components. It's only dealing with X components, right? It's only dealing with X components. But this Q, this source charge here, can be dealing with Y components as well. So we don't want any Y components from the source charge, and we want to make sure that the X components perfectly cancel out, right? So C is simply, you can just say between Q and the sheet, right? And you can draw that. That's it. Now, part D is going to be specifically asking us, okay, well, if it is between then where exactly? How far from the sheet is point B, right? And so, what do I want to say for this? Oh yeah. So we know that in order for things to perfectly cancel out, then the net electric field is going to equal EQ to the right minus E sheet to the left, right? And that has to be equal to 0. And effectively, that just means that EQ has to equal E sheet, right? What did I say earlier about which electric field is dependent on the distance? Which one of these is dependent on the distance away point B is? Exactly, right? The sheet is not dependent on the distance away the charge is, or distance away the point is, right? But the EQ is the point charge. And this is KQ over R squared with the absolute value around the Q, right? And we know it has to equal E sheet then. Well, this is pretty simple, right? So really, where you place it is only going to affect the magnitude of the electric field generated by the positive Q charge, right? So if we place point B closer to the test charge Q, or source charge Q, if we place point B closer to it, farther to the left kind of, then you would have a stronger electric field. If we place it farther away to the right, closer to the sheet, it's going to have a weaker electric field because the R distance is going to increase. So we want to find that sweet spot where we have a perfect R distance away that the electric field of the source charge Q just so happens to be equal to the electric field of the sheet. So we already figured out the electric field of the sheet, assuming the key is correct, and that was the 11.3 times 10 to the 6th, right? And now I'm seeing here, like, this is what I'm saying, like, it seems to me that these keys are just a little bit off, so I'm not entirely confident. Because I see here now they've plugged in the E sheet as 1.13 times 10 to the 6th. So I'm not 100% sure that this is right. I don't know if you guys have calculated this stuff out, but if you have an 11.3 times 10 to the 6th is right, then we're solid. So I'll just ignore the mistake that they made in part D. But yeah, so essentially we're just solving for R here because we want to find the R distance away that point B should be. So this is E sheet. So KQ over E sheet is equal to R squared, right? And then KQ over R, or over E sheet, and the square root of that is equal to R, right? K is your 9 times 10 to the 9. Q is your 2 times 10 to the negative 6, because that's 2 microcoulombs for that charge. And then E sheet should just be the answer that you get for the electric field of the sheet, right? So square root of 9 times 10 to the 9 times 2 times 10 to the negative 6 divided by, I mean, we from the based on the answer key, we got 11 times 10 to the 6th, right? But they have it on the key as 1.13 times 10 to the 6th, so I don't know who to trust at this point. And that's your R distance away from Q, right? So we're not done yet. Based on the answer key, they had it as 0.04 meters or 4 centimeters, right? So this would be 4 centimeters this way, right? But we know from a previous part, or from the initial part of the problem, that that distance, that total distance is 6 centimeters. We want to figure out how far it is away from the sheet. How can we do that? Because effectively, if this is, here's our Q, right? If this thing is 6 centimeters and B is located at 4 centimeters, then like this thing is 4 centimeters, then how far is B from the source charge, or from the sheet charge? 2 centimeters, exactly. So it'd just be 2 plus 4 right there. Or 6 centimeters minus 4 centimeters, that gives you 2 centimeters away from the sheet. So that's the R that you're looking for, actually, right? Just by solving this equation, you've only gotten part of the answer, because that just tells you how far B should be from Q, not how far it should be from the sheet. Does that make sense? Sound good? I'll let you guys process that for a second while I set up the next problem. Yeah, go ahead, Matthew. What's up? Yeah, absolutely. Is this good, or do you want me to zoom in or zoom out? And if you want to take a screenshot or a photo, feel free. And this document will be uploaded to the Google Drive as well, so you guys can see the work. I don't know if, yeah, go ahead. Sorry. Okay. Awesome. I don't know if you guys have watched the video. Doesn't seem like too many people have since last night, but I did do what I was talking about last night, which was I put the video through a AI program called Mac Whisper, and it uses like what's it called? ChatGPT's large language model to basically transcribe the video. The program was really really cool actually. I could just watched the video, and it transcribed everything that I was saying to a very large degree of accuracy, to be honest. So, um, those closed captions or subtitles are available on the YouTube video. So if you just click the CC button, you should be able to see exactly what I'm saying. So if you want to follow along that way, because I know sometimes you like to look at captions, I personally do. And then I uploaded that transcript, that entire transcript. I uploaded to the Google Drive as well, so you can kind of search for a specific topic or something, or for a specific problem, so you can figure out where I'm talking about something. But yeah, I don't know how helpful that is, but we'll see. Okay, so I saw some people typing earlier, but I don't know if you guys had any questions or not. No questions about the last one? Nope. Okay. Yeah, go ahead, Matthew. To which part? Oh, okay. This one right here, the 2 centimeter, 4 centimeter stuff? Okay, awesome. And let me read out the next problem as well. It says, picture shows charged parallel plates separated by distance d equals 2 millimeters with a uniform electric field between them pointing left of magnitude 2.5 times 10 to the fifth volts per meter. Okay. Electric potential is 0 volts at the left plate. Calculate the electric potential at point B, located 0.2 millimeters from the right plate. Right? So, okay, so they have an electric potential at that point at the left plate. We want the electric potential, or V, at point B, located 0.2 millimeters from the right plate. Okay. So that's not too bad. Let's see here. So So electric potential is another word for like your voltage, right? Your V. So they said the left plate is 0, right? We have the magnitude of our electric field, and we have the distance of the plate separation right here, right? Okay, what else do we want to do here? Calculate the electric potential at point B, located 0.2 millimeters from the plate. Potential energy is UE, yes. So electric potential energy is UE, and just electric potential is your voltage, your V. Yep. Okay. So really, what you have to understand here is when you are looking to calculate the potential at a specific point, we can't really, like, at least when you're looking at things between like two plates like this where you have a uniform electric field in between, you can't really find the electric potential at a specific point without referencing it to another point. So if you take a look at your equation sheet under the heading electric potential and potential energy, you'll see that there is the normal voltage equation that we know, which is KQ over R, right? But we're not dealing with a point charge here, right? We're dealing with two different plates here. They're kind of like sheet charges almost, that are generating an electric field, a net electric field between them, a uniform electric field between them. Now, if you notice, you'll see that the equation for the voltage in a uniform field is actually delta V. So the change in voltage between 2 points, right? And then that is equal to negative times the absolute value of the electric field between them times the distance, the parallel distance, just the parallel distance, right, between those 2 points. And by parallel distance, I mean, like, here's the thing. If I have a point here and a point there versus a point here, right, then these 2 points are separated by a vertical distance, a perpendicular distance, right? But it's not a parallel distance. They are the same parallel distance away from the positive plate. Would these two charges, 1 and 2, have the same electric potential? Would 1 and 2 have the same voltage, the same electric potential? Or would they have different voltage? It would be the same, right? And that's because, once again, the voltage is dependent on the electric field and the parallel distance away those 2 points are, right? So let's say here they might be separated by 2 centimeters, and this was separated by 2 centimeters as well, right? They are the same parallel distance away. They might be different vertical distance away, different perpendicular distances away, but they are the same parallel distance away, right? And because of that, they would have the same exact voltage or electrical potential. Now, these two charges, they are separated by some parallel distance away, right? So they would have different electrical potential. That being said, we're looking at this point B that's supposed to be like, what is it? 0.2 millimeters away from the right plate. And now we got to compare it to, like, we want to figure out VB, but we got to compare it to some other value. What other value are we aware of? What other voltage value do we know? V equals 0, right? The negative plate's electric potential. So we can say like VB minus VA, right? We call this point A right here, is equal to negative times the absolute value of the electric field between them, which they gave us, and then the parallel distance away from B to A. What is the parallel distance away from B to A? How can we figure that out? we know that the distance between the two plates is 2 millimeters, right? And the distance between here and here, the positive plate and B, is 0.2 millimeters. So now we got to figure out from A to B what this is, right? What would that distance be? .8 millimeters, right? And now you notice here that this doesn't have an absolute value around it. So we are actually concerned with the, what's it called? The sign here, right? And the sign here, the sign, is dependent on the direction of the electric field, right? Or at least, like, the, what's it called? What do I want to say? Okay, let me amend that statement for a second here. So, if you are traveling along the same direction as the electric field, then your distance is positive. That's fine. But if you are traveling in a direction opposite to the electric field, then that distance is going to be negative. Right? So that is the issue that we have here. Now, they don't really mention which direction you're moving in, but they do have a positive charge labeled in the diagram, and that positive charge has a little arrow to the right. So assuming that, we can see that the positive charge is moving in an opposite direction to the electric field towards point B. So that distance would be negative because it's in an opposite direction as to the electric field. So let me write a little notation here. D parallel, whether it's positive or negative, is dependent on if the movement is in the same direction or opposite direction to the electric field. If movement is same or opposite direction to electric field, right? So if it's positive, or if it's the same direction, right? Positive. If different or opposite, then it's negative, right? So we have this little positive charge here, and we're just going to assume that it's trying to move to B, right? So it's moving opposite to the electric field, which is pointing to the left. Because it's moving opposite to the electric field, the distance would be negative. If instead it was moving from here to the left like this along the electric field, it would be a positive distance because it's moving in tandem with or in line with or along the electric field. So VA, we already said that was 0 because that's the electric potential at that negative plate, and then this is equal to negative times the magnitude of the electric field, which was 2.5 times 10 to the 5th volts per meter, and then times the distance, which was that 1.8 millimeters, right? And that we have to convert to meters and also add a negative sign because it's moving opposite to the electric field. So negative 1.8 times 10 to the negative 3 meters. And let me move this stuff around here a little bit. Well, that wasn't good. So let me do this, do that, do this, do that, and do that, right? And then this is equal to, I believe, just based on the keys, 450 volts at that point. A lot of volts at point B. Does that make sense as to how to interpret that equation right there? And you'll see on your equation sheet that it says negative ED cosine theta. The reason why we're saying the distance moving with the electric field in the same direction is positive and opposite direction is negative is because of that cosine theta, right? That cosine theta, the theta or the angle here, is the direction between the movement and between the electric field. So if your movement is this way, an electric field is that way, this is 180 degrees. Cosine of 180 is -1. Right? But if your movement is in the same direction as your electric field, then angle is 0 and cosine 0 is 1. Right? So that's the idea there. So if your movement is along the same direction as the electric field, then it's positive. If it's in the opposite direction, then it's negative for your distance. So do not just plug in the positive value or the absolute value of the distance. Adjust it to show or reflect what direction you're moving relative to the electric field. But yeah. B, I think someone was asking earlier for a problem about like kinetic energy and whatnot. Here it is. There's something for everyone on these exams. This problem says a proton NP is equal to 1.672 times 10 to the negative 27 kilograms and has a charge of basically positive charge of an electron, right? It enters the space between the plates through a small hole in the left plate and travels to the right opposite the electric field. The electric force accelerates the proton to the left until at point B, the proton has no kinetic energy and starts to move back towards the left plate. Wow, this is kind of complex. So, goes through the small hole through the left, travels to the right, opposite the electric field. Okay, awesome. Then the force accelerates the proton to the left until at point B, the proton has no kinetic energy and starts to move back towards the left plate. Interesting. Very, very weird problem. So, yeah, use the plates again. Or not. So negative, 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 positive, 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 right? And we're assuming this kind of little hole right here. And the proton will move to the right, while the electric field is to the left. Right? So, part B wants us to calculate the initial kinetic energy of the proton when it enters the space between the plates. Initial kinetic energy. I mean, they said point B is where it has 0 kinetic energy, 0K. So essentially, kind of similar to what we were doing earlier, we have some kind of initial energy, some kind of final energy, right? Energy initial equals energy final, right? We had, let's say, some initial electrical potential energy based on our position relative to the plates and some initial kinetic energy. We had some final electrical potential energy and some final kinetic, right? Well, the final kinetic, they already said it was 0 because when you end up at point B, kinetic energy is 0, right? Now, let's see here. So we know that delta U is equal to Q test charge times delta V, right? Well, this delta U is the change in energy that we're looking for. UEF minus UEI, right? So we can rearrange this part of the equation here to be Ki is equal to UEF minus UEI. So that's just equal to our delta U, right? So what we're doing now is figuring out the change in voltage between the negative plate and point B, right? And we already kind of did that. Because we want to start off, let's say the voltage would be like V negative plate, or that's your initial. So we want to say VB, and we already defined the negative plate to be A, right? So we can say VB minus VA, basically. That's our change in voltage, right? Because we start off, that hole starts off at that negative plate, right? And then we just multiply by our charge here, right? And our charge is just the charge of an electron, or the positive charge of an electron, right? That's the charge of a proton. So that's 1.6 times 10 to the negative 19. Right? And this VB minus VA, well, we said that VA was 0, and VB, we already figured that out to be 450 volts. Right? So that's our change in the electrical potential energy that we observed. Right? And that's equal to some initial kinetic energy. So 1.6 times 10 to the negative 19 times 450 is equal to Ki. So you start off with your EI equal EF equation, right? You have initial energy, like some combination of initial energy, some combination of final energy, right? We know that our final kinetic has to be 0 based on the problem. They said point B. Like this is basically like saying like EA versus EB, right? EB, right? And at point B, they said there's no kinetic energy, right? At point A and B, though, there has to be, like, where we could at least analyze the electrical potential energy as well, based on their position relative to the plates, right? And then we see UEI plus KI on one hand, and UEF plus KF on the other hand. KF is 0, right, at point B. And then now we're just looking for, to figure out UEI and UEF, right? And we could pretty easily do that by rearranging the equation and figuring out the change in the electrical potential energy between those 2 points. Because otherwise, there's no real easy way to do it because we don't have point charges, so we can't just use KQ1, Q2 over R. Because we don't know, like, you can't even do it because you're not dealing with point charges. You're dealing with, like, sheet charges, essentially. So you have to look at delta U is equal to Q times delta V, right? You can't just use the potential at one point to figure out the electrical potential energy at that same point. You have to find it between 2 points, the change between 2 points, to figure it out properly. So we can use that reference point at that negative plate to be 0 to figure things out. But yeah, and you can just do that in your kinetic energy initial based on, once again, the answer key should be like 7.2 times 10 to the negative 17 joules is what it looks like to be. Does that make sense so far for B? And I can't remember who asked earlier about like kinetic energy stuff, but like, is it starting to make sense like how we can relate this, like the old energy stuff from 131 to this 132 stuff? Okay, awesome. Part C, calculate both the proton's kinetic energy and electrical potential energy at point A, halfway between the plates. So proton's kinetic energy and the electrical potential energy at point A. So this is once again really just doing part B, but referencing a different point, right? So like I can't really use A at this point again because we already have a point A. So we'll say like E negative is equal to EA, right? Like and by E here, I don't mean electric field, I mean like energy. Like energy at negative plate is equal to the energy at the, at point A, right? That's going to be a sum of UE at the negative plate plus kinetic energy at the negative plate is equal to some energy at A plus some potential energy at A plus some kinetic energy at A, right? Well, at A, that's the kinetic energy that we want to figure out, right? We already figured out the kinetic energy at the negative plate, which is technically our initial energy here, right? Which is what the charge was coming with, essentially, right? So this is our 7.2 times 10 to the negative 17 right here. For our energies, though, once again, we can find the change in energy, UEA minus U negative, right? That would be the delta U, basically, right? So K negative is equal to UEA minus UE negative, and then plus Ka, which is what we're trying to figure out. And this becomes delta U plus Ka is equal to K negative, right? And delta U, we can figure that out by taking Q times delta V, right? So you just take the charge of that proton times the change in the voltage between them, right? Now, changing the voltage between them, we also have to figure that out. So let me write this up as, this was 7.2 times 10 to the negative 17 on one end. And this is the Ka that we're trying to figure out. This is Q times Va minus V negative plus Ka. But what is Va, right? How can we figure that out? Well, we can use the negative times the absolute value of the electric field times the parallel distance away equation, right? So we know that the electric field had a magnitude of 2.5 times 10 to the fifth, right? And the parallel distance away, well, this should be negative once again because we're moving opposite to the electric field. And it should be the exact half of the distance between the two plates because it says A is halfway between the two plates. So if it's 2 millimeters, the distance between the two plates, then this is 1 millimeter, right? So let me adjust this, move it over here, right? And this would be negative 1 times 10 to the negative 3 meters, basically, which is the same thing as 1 millimeter. If you do that, I believe you should get like 250 volts, right? So that's our A. Here's our Q again, here's 250 volts, and this is 0 because that was the voltage at the left plate, and then plus Ka, which is what we're trying to figure out, and then this Q right over here is just the charge of the proton, which is 1.6 times 10 to the negative 19, right? So now it's just a matter of solving, isolating, doing all that, and solving for Ka. If you do that, Ka should be, based on this equation, based on the answer key, 3.2 times 10 to the negative 17 joules. But yeah. Let me just double check this. Okay. Okay. Boom, boom, boom. Yeah, I think so. This looks good. Yeah. All right, and then that's problem 8. I'm going to set up problem 9. Let me know while I'm doing that if you guys have any questions about problem 8. Yeah, so the 7.2 was the initial kinetic energy from the negative plate, like when the proton is coming in. And so we're using that basically, which is just the kinetic energy at the negative plate when the proton enters the hole. Yep. And that makes sense as well earlier, like how we figured that out, like the initial kinetic energy and stuff. Or is that still confusing? You're good now? Okay, awesome. If there aren't any other questions about problem 8, we can move on to problem 9. So problem 9 is a capacitor consists of plates with an area A equals 10 centimeters squared, and they're separated by a distance of 1 micrometer, right? So the distance between the capacitor plates is 1 micrometer, and the area is 10 centimeters squared. For A, they're asking me to just calculate the capacitance of the capacitor, right? And the equation for the capacitance, if you look at your equation sheet, you'll find that the equation of the capacitance is the permittivity constant times the area divided by the distance between the two plates. This is a very easy plug and chug type question, right? So this is your 8.85 times 10 to the negative 12 times your area, which is 10 centimeters squared. You want to convert that 10 centimeters squared to meters squared. This is like 10 times 10 to the negative 4 meters squared then. And then divided by the distance, right? And that was 1 micrometer, so 1 times 10 to the negative 6 meters. And if you're wondering how I got 10 times 10 to the negative 4 meters squared, well, 10 centimeters squared, right? There are 100 centimeters in 1 meter, and then you have to square this whole thing, right, to be able to get like meters squared on top and centimeters squared to cancel on the bottom. But yeah, and your capacitance then, I believe, should be 8.85 times 10 to the negative 9 farads. I don't believe they would ask you to convert it back into like microfarads, or in this case probably like nanofarads. So I would just keep it as farads because that's probably just easier, because you're going to use that as the SI unit afterwards. But yeah, and then part B, it's saying the capacitor is charged by a battery with the potential difference voltage 24 volts, right? Calculate the charge on the plates. Well, voltage, charge, voltage, voltage, charge, capacitance, capacitance, charge, voltage. There should be an equation that will relate these concepts together, right? And so if you look at your equation sheet under the capacitor's heading, it's very easy. Q equals CV equation here, right? So we want to figure out the charge on the plates. We can multiply the capacitance of the capacitor times the voltage across that capacitor. That gives us our charge. So we have that 8.85 times 10 to the negative 9, and then multiplied by the voltage, which is 24 volts, and that should give you like 2.12 times 10 to the negative 7. Once again, this is all based on the answer key. Alexa, I saw you typing. Do you have a question? Gotcha, okay. But yeah. I don't know why I froze there. Like I was just like dead silent, just staring at my computer for like 10 seconds. Part C is asking how much energy is stored on the capacitor. So now we're just looking for the potential energy, right, stored across the capacitor. This also warrants use of another equation under the capacitor's heading in the equation sheet, right? So electrical potential energy is what's being stored, and there are different equations for it, right? So you have 1/2 times QV that you could use. You could use the charge from part B multiplied by the voltage across the capacitor. You can get that. That'd be done. Then you'd be done, right? So we do 1/2 times QV, 1/2 times that charge, and then multiply by the 24 volts. That should give you your electrical potential energy. 2.54 times 10 to the negative 6 joules is what they had. Once again, I'm just going by the answer key. That's what it was. But yeah. I saw someone else typing a couple of seconds ago. Did you have a question? I don't know if it was one person or multiple people. One half CV squared should be able to give the same answer as well. Yep. Any other questions about part C? Okay, awesome. And then part D is saying a second identical capacitor is connected and filled with a dielectric. Kappa is equal to 5.4. How do each of the following quantities compare between the two capacitors? Well, first of all, when you have a dielectric placed between two plates like that, what does that do to the capacitance of a capacitor? Because a dielectric could also be thought of as an insulator of charge. And capacitance is kind of defined as like the ability to store charge, right? So there's an equation. I don't think it's on the equation sheet, but how can you figure out, or essentially what happens if you place a dielectric or an insulator between plates of a capacitor? What does it do to the capacitance? It doesn't necessarily double it. It could double it. It increases the C, right? Generally, it does increase. Yes, absolutely right. It could double it. It doesn't have to double it. But the capacitance is directly affected by a dielectric constant, right? So they gave us that dielectric constant, kappa is equal to 5.4. That's a dielectric constant. So if I place a insulator or a dielectric between two capacitor plates, right, then I can figure out the new capacitance by taking that dielectric constant right, and multiplying by my old capacitance. So in this case, it's 5.4 times my old capacitance, right? My old capacitance was what? It was like 8.85, wasn't it? Times 10 to the negative 5 farads, right? So 8.85 times 10 to the negative 9 farads, and that would give me my new capacitance, right? So, the reason why we have to adjust for this is because this new capacitance is going to change this equation up. Q equals CV. Now it's not Q equals CV, it's Q equals C nu V, right? So it's C with a dielectric, right? So that'll drastically affect what's going on here, right? So if we have this capacitor set up like this, or these capacitors here, we have this battery of 24 volts, and you have capacitor here. If it'll just, straighten out my line, there we go. And a capacitor there, right? But now this one is filled with a dielectric. So this is C2, this is C1. Real quick, just to test you guys if you have been paying attention to the resistors, capacitor stuff. Are these two capacitors connected in series or in parallel? Parallel, right? Because there's a branch point. Because if we follow the current from the battery, we go up here, we experience a branch point, right? Where the current could be split into C1 or in C2. So these branches would be in parallel. So these are connected in parallel. With that in mind, capacitors in parallel, what do we know about their voltage? Capacitors in parallel. What would their voltage be? Would they increase, or would it be the same? Or exactly, it would be the same, right? So for that first condition, V2 is equal to V1 because they're connected in parallel, so they should have the same voltage, right? Now, we look at the net electric field between the two plates. So with a capacitor, and I think I have a feeling this might be incorrect on the key, if you guys have taken a look at this before. But maybe I'm just missing something. But for a capacitor will generally kind of weaken a electric field, like an electric field between the two plates like that. because the dielectric material itself, despite being an insulator, will have like charges on the inside, and those will oppose the field of the capacitor, right? So let's say like the capacitor electric field is pointing this way. Once you place a dielectric inside, it'll oppose the electric field, so it'll weaken it. So I think, if I'm not mistaken, in that case, E net 2 should be less than E net 1. But let me double check here. I'm going to go back to the reading just to make sure. Readings, okay. I'm fairly certain that that's the case. Okay, so I think it's on page like 23, right? Page 23 of the reading, chapter 10. Yeah, I think that's right. So you'll have an electric field due to the charged plates of the capacitor, and you place a dielectric in between, it'll oppose that electric field and reduce that electric field. So E2 should be less than E1. From what I'm understanding here. Capacitors are both the same. Yeah. Yeah, I think E2 should be less than E1. Does anybody see any like error in my logic? I guess not. All right. Now when we're looking at charge, right? Looking at charge. Well, once again, Q equals CV. The voltage across them has to be the same. So this one has 24 volts, this one has 24 volts, but the capacitance is different, right? So this capacitor has increased capacitance because of the dielectric. So we'd be taking 24 volts times a larger capacitance. And so Q2 would have to be greater than Q1. So Q2 greater than Q1 based on that equation. Does that make sense? Okay. So that's problem 9. Problem 10 is some circuits, some resistors here. So this is R2. Here's R3 and R4, right? And here's R1. Here's your positive terminal, here's your negative terminal, 24 volts, 0 volts on the other end. And the current moves this way, obviously, right? So, and we have this point B that they want us to label, and this point A that they want us to label over here. Or, should be over here. All right, so part A is asking us, determine the equivalent resistance of all 4 resistors. So, what does that mean? What are they asking for when they want us to find out the equivalent resistance of all 4 resistors? Come on, guys, bear with me. This is the last, stretch. You add them all up, right? You have to simplify all the resistors together and combine them into, what I was talking about earlier, this pseudo, pseudo-combined resistor, essentially. What would we label that resistor as? Because remember, you have to like really kind of label this stuff. So if I had one huge combined resistor of all of these resistors, what would I label it as? So excellent. So you actually did a really good job, and I think you're really understanding what's going on here, because there's one step left, but you're on a really good track. So you said R234 plus R1, right? So R234, I'm not gonna like go into why you said that, but if you're adding now R234 and R1, what would be the combination of those? Well, I won't say if they're in series or not. We won't do that yet. But if I'm just combining two resistors, one of them is called R234 and the other is called R1. If I combine them together, what should my final combined resistor be? What should it be called? Well, RS would just be like if you have resistors in series. Not 1 over R. Like you were really close. You had R234 and you had plus R1. So imagine if those two resistors were together and we wanted to simplify them down even more. So exactly, R1, 2, 3, 4, right? So that is the pseudo combined resistor if we would add up all of them together, right? So in order to add them up together, we got to go through, look at which ones are in series, which ones are in parallel, right? So remember what I said earlier, you kind of trace your circuit, trace your current through here. Okay, we see R1, this is our tree trunk right here. We encounter a branch, awesome. Do we encounter any sub branches? Yes, here's a branch point. Right, here's a junction, here's a branch point. Any sub branches here are going to be in parallel with one another. All right, how can we simplify this down? Well, we have R2, that's on one branch, and we have R3 and R4 on the other branch. How can we simplify this down? What's the relationship between these two resistors? What's the relationship between these two resistors, R3 and R4? I was saying, what's the relationship between these two resistors, R3 and R4? Like, are they in series? Are they in parallel? What's going on here? R4 and R3 are in series, actually, right? Because they're consecutive. There's no branching between them. So between R3 and R4, like in this little distance here, there's no extra splitting off of the current. They're consecutive, right? So if even like, here's the thing, like if you want to think about this instead of just like branches and stuff, you can think about it like as, what's it called? Episodes in a TV series. Here's episode 1, right? And then after episode 1, some kind of like huge crossover event is about to happen. Like this was, I don't know, The Flash on the CW. Here's episode 1, whatever, right? Or it's like, let's say episode 10. I don't think they do like their crossovers like midway through the season or something. Here's that's episode 10. And then you get to like episode 11, you're like, well, now I have to watch Supergirl. Now I have to watch, you know, what's it called? Not Green Lantern, The Arrow. And I have to watch all this other stuff, right? So it's like this crossover event that you have to keep track of. And so then you have these two episodes that are consecutive to each other. Let's say maybe like this might have been Supergirl episode 12, part 1, and then part 2, right? Now they're consecutive, but they're part of a crossover event. That's another way of thinking of it too. This is all like very goofy, so I don't know if this is making any sense or if we can just go back to trees, but considering series like TV series, I thought I might also throw that out. So, I don't know. But anyway, R3 and R4 are in series. That's absolutely correct. So we can simplify these down to what? What would be the simplification of R3 and R4? How would we label that? R34, right? R34. So we got to figure out what R34 is. You actually have to show every single step of simplification here. So R34, since they're in series, it's just R3 plus R4. And they told us that R3 is 4 ohms and R4 is 6 ohms, right? So this is just 10 ohms, right? Now we got these two branches, right? R2 and R34. Are these in series or are they in parallel with each other? Excellent. R34 and R2 are in parallel, right? Because you branch off. This is a sub-branch and this is a sub-branch, right? You go from watching The Flash to watching Supergirl and an episode of The Arrow, right? So R2 and R34 are in parallel. So 1 over R234 is what we're trying to get, right? That combination there would be 1 over R2 plus 1 over R34, right? Well, R2, they said that was 10 ohms. And R34, we already discovered that to be 10 ohms as well, right? So this is just 2 out of 10 or 1 over 5, right? And that's only equal to 1 over R234. So R234 is actually equal to what? What is it actually equal to? 5, right? You take the reciprocal of that answer. Does that make sense where we got that? Okay, awesome. So now we have R234, and now we have R1. Awesome. We go back, we trace the current, R1, here's our branch, our trunk, still on that same branch, back to the battery, no extra branching points. Everything is in series, right? So we can now figure out R1, 2, 3, 4, which is our equivalent resistance of all 4 resistors. Add them up. So that's just R1 plus R2, 3, 4, which is what Alexa was looking at earlier. And that's really good because you actually, I think you recognized early on that R3 and 4 were in series and R2 and R34 were in parallel. So you actually solved this conceptually very early on, which is excellent. Bravo. So R1 plus R234, so that's 5 ohms, right? Plus R234, and we figured out that R234 was 5 ohms as well. So this is just 10 ohms. The whole thing is 10 ohms. And here's my question to you guys. I mean, it is kind of a lot of work for 3 points, but I don't know. I like circuits a lot. I like simplifying this stuff down. It's kind of satisfying going from all these different branches to one simplified thing. It's pretty cool. I don't know if you guys share the same sentiment, but yeah, I was wondering if you guys also think it's satisfying to simplify these circuits down. Maybe I'm just a nerd or a geek. I don't know, but I just really enjoy doing the circuit stuff because it's not hard math. The concept is a little bit hard, but it's really nice when you see it's a really dumb circuit and you kind of simplify it down. So yeah, I personally like this is my favorite stuff of everything in physics. But yeah, B is saying the battery has a voltage of 24 volts. Calculate the current through the battery. So we just use Ohm's law. Very, very simple. So we know that the battery is 24 volts. We know now that the resistance of the whole thing, R1, 2, 3, 4, right, is going to be, what's it called? 10 ohms, right? So now we want to find the I, or the current of the whole thing. So we know that I times 10 ohms is equal to 24 volts. So the current is 2.4 amps, and that's it. Very, very simple right there. Now, what did I want to say? Here's another thing. So let me just double check this real quick. Yeah. You cannot, I don't think, very just easily go ahead and say, okay, well, the battery has, like, for example, let's say you had no clue how to do A. And you go and you skip to part B. And you're like, okay, well, battery has 24 volts. I want to find the current, right? And you're like, okay, well, I have a resistor, R1. I know R1 is in series with the battery, right? So couldn't I just do 24 volts is equal to I times the resistance 1, so 24 divided by 5? No, you cannot do that. Why? Because, once again, these resistors drop the voltage from the initial battery, right? They will each have their own unique voltage drop. So 24 volts is not the voltage at R1. In reality, once you go check this, 2.4 amps times the resistance at R1, 2.4 times 5 gives you 12, actually. 12 volts across R1. So you can't just solve that like that. I mean, the most I think you would be able to get is partial credit for writing down Ohm's law and then solving for a current that way. Like, you might get like 1 point or half a point or something for like writing down the equation and solving actually for something, but you have to recognize that you can't just do that. You can only like figure out the overall current, right, by simplifying the battery or simplifying the circuit down. And then once you have the simplified circuit, you could use the voltage of the entire battery divided by the resistance of the entire circuit to get the current of the entire circuit. And then with that current of the entire circuit, you can multiply across different resistors to get the voltage drop across each one. Now, here's where it gets a little confusing though. So I know that it's 2.4 amps, right? That's my current. 2.4 amps times 5 ohms for resistance 1 gives me 12 volts, right? But for resistors in parallel, what do we know about the voltage of resistors in parallel? What is unique about the voltage for resistors in parallel? They are the same, actually. So voltage for resistors in parallel are going to be the same. So like when we initially simplified down R3 and R4, R34 would have the same voltage as R2. They would have the same voltage because they have the same common input point connection and output point connection, right? So R2 and R34 would have the same voltage, right? Now, how can I get the current going across each one, right? Well, I have to notice that, like I said earlier, the voltage drop does not split between them, right? R2 doesn't get a certain voltage drop, and R34 doesn't get a certain voltage drop. They have the same voltage drop, right? So if I simplify this down to R234, I should still have the same voltage drop across the whole thing, right? Because they're in parallel, so they should have the same voltage, the same input point, same output point, right? So R234, I can then figure out the voltage drop across that one, right? So I had 24 volts initially, right? And then I subtracted the voltage drop for that first resistor, so I times R1, right? So this was what? 2.4 amps times the resistance for R1, so 5 ohms. 24 volts minus that is 24 minus 12, so that gives me 12 volts left over, right? Well, since I simplified that circuit down to R234, right, then I know that R234, that is the only combined resistor left, or the only resistor left, so it has to have that other 12 volts. It has to drop that other 12 volts in order to then effectively, like, quote unquote, get recharged by the battery at the end, right? So I had 24 volts, 12 volts got dropped off here, another 12 volts had to get dropped off here. So that now that it's 0, I can recharge again, right? That's the idea. So now I have this 12 volts. So I'm like, all right, well, I have 12 volts across R234. That means that R2 has 12 volts, right? And R34 has 12 volts, right? So, with that being said, if I wanted to figure out the current going through R2, I would say, well, V equals IR. That's 12 volts. My current, right, is unknown. I want to figure out how much that current split by, because I'm coming in with 2.4 amps, but it gets split between R2 and R34. So I want to figure out what this current is, this I2 basically, and multiply it by my resistance, R2. So that's 10 ohms, right? So in reality, I2, the amount of current that went through R2, the amount of current that branched off to R2 was 1.2 amps, right? R34 then also got 12 volts. I34 times that combined resistor was what? R34 was 10 ohms, right? So it got 1.2 amps as well. So the current was split evenly between the two, perfectly, right? And so now I'm like, okay, I have I34 is 1.2 amps. What did I say about R3 and R4? What's the relationship between R3 and R4 again? In series, yes. So if they're in series, what does that mean about the current between them? If they're in series, what does that say about the current? The current is the same. So R3 has I equal to 1.2 amps, and R4 also has I equal to 1.2 amps. Right? To where that if you were to like trace this back, well, I don't have the original drawing, but you get the idea. Like if you trace this, 1.2 goes through R2, and 1.2 goes through R3 and R4, and then the 1.2s from each branch join together back at point A to make up 2.4, which is the original amount of current that you came in with, right? So I kind of went off on a tangent here just to like show you how you can figure out the current going through each resistor and then the voltage drop across each resistor. So knowing that 1.2 amps is going through resistor 2, right? I can check it. 1.2 amps times resistor 2, 10 ohms, that's 12 volts, right? How about R3 and R4? Well, R3 and R4, 1.2 amps times R3, right? That's 1.2 amps times 4 ohms, that's 4.8 volts. And then 1.2 amps going through R4, right? That was 6 ohms. That's 7.2 volts, right? 7.2 plus 4.8, that's 12 volts. And then you can see I have 12 volts on the top, 12 volts on the bottom branch, right? That confirms that the voltage should be the same across resistors in parallel, right? So R2 has 12 volts, and then R34 has 12 volts as well. And then when you simplify them down to R234, you still have 12 volts across that combined resistor of R234, and then 12 volts from R234 plus 12 volts from R1 is 24 volts that was delivered from the battery. So that was B. C is saying use the loop rule to determine the current through R2. You kind of already did that, didn't we? Right? So we know that voltage of the battery coming in minus the voltage drop across R1. That was I1 times R1, right? And then what do I want to say here? So minus I2 R2, right? And that should equal 0. Why should it equal 0? Because, once again, like we said, the voltage across resistors in parallel should be the same. So R2 and R34 should have the same voltage. And then R234 should have whatever voltage was remaining after that voltage drop from R1. So just by looking at this first, this was 24 volts minus that 2.4 amps times R1, which was 5 ohms, right? This is 24 volts minus 12 volts is equal to 12 volts, right? So this tells me that R234, whenever I combine that, that should have 12 volts. And then the components of that, like the two branches, R2 and R34, right? So this means R234 is equal to 12 volts. Also means parallel branches R2 and R34 equal to 12 volts each, right? Because the voltage would be the same across them. So given that, right, then I know that because V equals IR, right, then I2 R2 has to be equal to this 12 volts, right? I know that. And because this is equal to 12 volts and this is equal to 12 volts, then 12 volts minus 12 volts is 0, and that's why I set the equation equal to 0. So once I have that, right, minus RE2, actually let me just rewrite it down at the bottom. So I have this, what do I want to say? V battery minus I1 R1 minus I2 R2 is equal to 0, right? So this is 24 volts minus that 12 volts from R1, and then minus I2 times the resistance of R2, so 10 ohms, and that's equal to 0. So this is 12 volts here, and then it's equal to I2 times 10 ohms, and then you can see that I2 is equal to 1.2 amps, and then boom, you got your answer there for C. Now for D, right, it says use the junction rule at point A to determine the current through R4, right? So point A, the junction rule, like the branching rule, basically, right? So point A, once again, like honestly, I kind of just solved all of this really already, but to just take it step by step, right? So we have the current through R4 is what we're trying to figure out, right? We know that the current going through I2 should equal to 1.2 amps, right? I2 plus I4, the current going through I4, should equal that 2.4 amps. Why? Because they're coming together to reunite to that original amount of 2.4 amps, right? So 1.2 amps was delivered to R2, 1.2 amps was delivered to R3 and 4, right? And so they have to reunite at point A, at that output point, at that junction, right? Where was that that point right here, right? They had to reunite. So if I had 1.2 going through I2, through resistor 2, and I have 2.4 that needs to come out of A, then I can just say 1.2 amps plus I4, because I4, resistor 4 is the last resistor that the current has to go through to get to A in that bottom branch. So this is equal to 2.4 amps, and then I4 is simply equal to 1.2 amps. Boom, done. Right, and that's because R3 and 4 are in series. We kind of explained that earlier, right? Finally, E, which is calculate the electric potential at point B, right? They want us to figure out the electric potential at point B. So really, this is just asking like how much voltage is at point B. And point B was right after R1, but before the branching of R2 and R3 and R4, right? So this is just asking you like, okay, how much like voltage essentially do we have left basically, right? Because we know that V battery, right, we started off with 24 volts and we only went through one resistor. This is the resistor of R1, right? So I1, R1. So 24 volts minus the current through 1, that was the 2.4 amps, right? Because the current has not been separated or broken off yet. So 2.4 amps, and then times resistor 1, that was 5 ohms, right? So that's your 12 volts here. So 24 minus 12, and that would give you 12 volts, right? So that is your electric potential at point B. Right, so VB is equal to 12 volts at that point. So that's the amount of voltage effectively left after dropping voltage at resistor 1 and before branching off and dropping more voltage for R2, R3, and R4. So that is the gist of that practice exam. Not really a gist. Just 3 hours is not a gist. But I'm going to go ahead and end the recording on that note because that is all for the practice exam. Time is up pretty much for the review session that I had allotted. But yeah, if you guys have any other questions, only like 3 people left. So feel free just to like DM me and let me know if you have any questions. I'll be happy to answer. But hopefully you guys found this review session very helpful. So yeah, thank you guys for sitting down with me and doing these problems. I really appreciate it. Appreciate that you guys came out, and hopefully you guys do well in the exam.